Hey all, today we will understand what is logistics regressions and how it works and what are the assumptions behind it and what is the mathematical formulas behind it. So the first assumption that we have in logistics regression is that the outcome has to be binary. It has to be yes or no. For example, in email classification, the email is either a spam or not a spam. Second assumption that we have is features are linearly related to the log of odds. Now, what does it means? It means that the output of our algorithm and the features of our algorithm are linear with log of odds. So, odds we know, let's say p is a probability of something, so odd will be p upon 1 minus p. So, let's say India has a chance of 60% winning a match. So, losing will be 40%, so it will be 60 by 40. This is odd. So when we take log of it, that means we are taking we are taking standardizing it, and then after standardization or normalization of it, when we check with the features, it has to be linear. So this is the second assumption. The third assumption is there should not be multi-collinearity among the features. So let's say there are 10 features to predict something. So they should not be collinear with each other. That means when you we know the formula for correlation. So when you check the correlation between them, the correlation should not be more than 0.4 or 0.5. If it is higher than that, then you have to apply some formulas like principal component analysis or something, but you have to reduce this multi collinearity or drop some features. The fourth one is large sample size preferred. So this is like a common among many algorithms. So larger the sample size, the better is the output of the algorithm. So now let's move on to next topic, that is linear regression recap. So we all know logistics regression is kind of an extension of linear regression, where linear regression predicts output on a particular line where output can be between minus infinity to infinity. What does logistics regression does is it squishes the output of linear regression to 0 and 1. So we know like this formula y is equal to wx plus b, a common formula used in linear regression, which is like our school formula for a line, which is y is equal to mx plus c. So this will give output, it can give any output for y, and then we do all the loss function, we calculate loss function, then cost function, and then gradient descent, and then we reach to our output. But if we want our output in binary format, let's say yes or no, 0 or 1, then we have to squish our output. Now how we can squish our output mathematically, we will understand here is, so there is a function which is called as sigmoid activation function. So here we will see how we will move from a linear model, which is linear regression, to a sigmoid activation function. So let's just see these two graphs. The left hand side graph here shows that a simple linear line z is equal to wx plus b, and it shows that the values of it can be from negative infinity to positive infinity, and this will be a straight line, so assumptions will be different. Now let's see the right hand graph. Here my output is between 0 and 1, and this is not like a straight line. If you can see, it is like a curve output. And if you see the values, this starts from 0 and then it reaches maximum up to 1, 0.99, and then it goes to 1, but it will not move beyond that. So this is the function that will convert our linear output to a non-linear via sigmoid function. Now let us understand how this sigmoid function works and why the sigmoid function output is between 0 and 1. So let's understand mathematically. The formula for sigmoid function is 1 upon 1 plus e to the power minus z. Now here e is our Euler number and z is our wx plus b, where w can be your weight and b is your bias. In simple terms, w is slope of your line, and b will be your where the intercept of line is at y axis. Now when we put this normal wx plus b in z, we will get an output which will be between 0 and 1. How? E is Euler number, which is something 2.18 something, I don't remember exactly now. But when you apply this formula here, e to the power minus z will be something a positive real number, and when you add up with the 1 plus, that means 1 divided by something which is greater than 1, that means our value will be between 0 and 1. So that's what this sigmoid function signifies here. So yeah, we can see on screen here 1 plus e to the power minus z will be greater than 1, which means our sigmoid of z will be between 0 and 1 for all the values where z belongs to real numbers. Now let's move on to our next topic in logistics regression, and we will see what is the loss function formula applied in our logistics regression. So we all know in linear regression the formula for loss function applied was mean square error. But here, since the model is moving more towards a probabilistic model, we are going to apply a concept which is called as binary cross entropy. So in binary cross entropy, the formula for loss function is minus of y to the log of predicted y plus 1 minus y to the log of 1 minus predicted y. Now this is the formula, just understand. In next step we will also see how we are reaching to this formula. Basically we are deriving this formula. So let's move to the next slide. So yeah, we will need a loss function that penalizes the wrong confident predictions, and binary cross entropy does that. So basically what it's saying is, when we have an output, we will need a function. If our prediction is far away from output, we need something which will penalize it. Now let's see how it works. So here if you see y is equal to 1 and predicted y is 0.9, that means loss is our minus log of 0.9. Minus log of 0.9 is a very low number. That means we are very close to our actual output. So smaller the loss when prediction is close to the actual label. That's what it signifies here. So now let's see how the binary cross entropy loss formula is derived. Now let's see here, sigmoid function says the predicted y, that means sigmoid of z, is equal to 1 upon 1 plus e to the power minus z, where z is equal to wx plus b. Now let's see the next thing. The Bernoulli likelihood function says that probability of y when x is true is equal to y predicted to the power y dot 1 minus y predicted to the power 1 minus y. Now this is a very important formula to reach our final loss function formula. Why this is very important? If you see the probability of something, in binary classification it will be either 0 or 1. Now let's say the probability of something is 0, that means we will apply y is equal to 0. Now let's apply here y is equal to 0. So first y predicted to the power y is becomes 1, because anything to the power 0 will become 1, and next thing will become 1 minus y to the power 1 minus 0. So here what it will become is 1 minus predicted y. So when it is 0, it will become 1 minus predicted y, and when it is 1, so if we apply 1 in this formula, y to the power 1 will become y predicted dot 1 minus y predicted, 1 minus 1 will 1 becomes 0. That means this entire second part of the function will become 1. So it will become y to the y predicted to the power y. So that means if probability of something is 1, it will be the first part, and when the probability of something is 0, it will be the second part. So rather than writing it in a case when statement, this particular statement integrates everything in a single statement. That's what it symbolizes. Now let's see next part, the log likelihood. What it is doing here is the Bernoulli thing that we saw just now, we are now applying to the log of it. Now when we apply log to the entire function, what it becomes is log of p y when x is true is equal to log of y predicted plus 1 minus log of 1 minus y predicted. Now this is our loss estimation formula. Now this is for a single feature, single point. But when we apply to the all the samples, let's say we have n samples and we apply this formula to all the samples. So what it becomes is 1 I is equal to 1 till n summation, and then the same formula that we saw in last slide, it is yi log of y predicted I plus 1 minus yi log 1 minus y predicted I. So in simple terms you can understand, like, we are comparing actual values and predicted values, and we are getting a loss. Now what will happen once we get the loss? So next step what will happen is a gradient descent. Now gradient descent we have already seen in linear regression, that the ultimate aim of our getting loss function here is, once we have the predicted value, we want to see how far it is away from our actual value, and based on that we will take the derivative of that particular thing with the weights of our function, and then we will minimize the loss function in the next step. So let's see the next step now. So this was the derivation of binary cross entropy. Let's see how gradient descent works. So here if we see, what happens is w of 0 is equal to 0.4. So in first step it will randomly assign a value to the 0. So let's say y is equal to wx plus p. Randomly it has assigned a value here to w, and then it is calculating my z. Once it has calculated my z, I will apply a sigmoid function to it, and I will get my value of the y predicted. Now my value of y predicted here, let's say, is 0.5987. Now I will calculate my loss function. So here, based on this value 0.5987, when I calculate my loss function, it says the value is 0.9130. Now in next step we will see how this thing we are correcting. So the next thing is, we are taking the derivative of loss with respect to weight, which is y predicted minus y dot x. So here it means is that the loss is not that much. Loss is there, but loss is not that much. So we have got the value of derivative of loss with respect to weight. Now what we are doing is, we are getting a new weight. The last weight had some loss. Now we want to calculate new loss. So what we are doing is, weight 1 is equal to weight of 0 minus n. This is a learning rate. So learning rate can be 0.1, 0.2 based on your problem statement. You can define the learning rate, and then we are multiplying our learning rate with derivative of loss with respect to weight, and we are adjusting our weight. So what ultimately we are doing is, we are adjusting our weight, and then this particular weight 1 will again go to that formula where z is equal to wx plus p. So this is like a loop where our weights will be recalculated again and again till the time our output converges to a point where the loss function is getting diminished, and weights are also converging to a particular point. Then we can say that is like our actual predicted point. So this is what gradient descent does after we have calculated our loss from binary cross entropy. So let us quickly recap everything whatever we have learned in this video. So first we saw the assumptions. The output has to be binary. The log of odds relation, linear log of odds relation, basically it says that your features should have and your output should have a linear relationship when we take the log of odds of output. Then third is, there should not be a multicollinearity, and fourth one was that the data sample size should be very large. The next thing we learned about was linear model. So how linear regression is working, because 60 to 70% of logistics regression is our linear regression itself. The only part is when we squish the output and take the loss function and calculate it further. That's where logistics regression actual formulas comes into picture. The third thing that we learned in this part was what is a sigmoid activation function. So once we learned the linear model, the next thing was, in that linear model we applied the sigmoid activation function, whose formula was 1 upon 1 plus e to the power minus z, and that maps our values to the real numbers between 0 and 1. So whatever your output was, that has been mapped to 0, 1, and basically saying yes or no, then falling it in a classification category. The next thing we did was calculate a loss function. So here we used binary cross entropy. In linear regression, mostly mean square error method is used, but in logistics regression, binary cross entropy is a more common method. And then we saw how binary cross entropy loss function, how we derive this particular loss function. So that derivation we saw here. And then last thing was how we are taking the gradient descent of it, how we are taking the derivative of loss with respect to weights, and then we are again and again recalculating our weights, and then how we are reaching to the correct value. So this is what we have learned today. I hope you guys liked it. Thank you. We will learn next algorithm in our next video. Till the time, goodbye.